Oh, spoon
Manchester shopping. Laptop change.
Okay.
सबसे अच्छा लगता है वो देखने में. And I like Lenovo actually. But my work laptop is a Lenovo. I like this.
Okay. I will.
You know, all flashing. Hard disk. That's right. See, we will just for
Okay, fine. So I'll start and we'll do graphs today, or attempt to do graphs today. And well, like I don't think most of you know that I was actually not a dev at Microsoft. I was a test at Microsoft, and yeah. So, but I didn't like Microsoft enough. After working for 5 years, and I was like, okay, now it's 5 years, I got my bonus and everything that was given, now I should leave. And I left, and my reviews weren't exactly great. So, like, I had problems with my manager. So, it's much better to be outside Microsoft, I guess. So, that's what I feel. Like, I don't know how other people feel, but Microsoft is. Yeah. Anyways, okay.
Yeah, I'll probably totally agree with you. Even though I'm getting good reviews, but I don't like the system actually. Encourage the work. I was actually discussing that one just now.
I'm not working on myself anywhere.
Yeah.
You are. You are.
Why are you in the class then?
Just need to brush up actually.
No, but I will not.
You know, like when you,
This is not. This won't be available to anybody else. Don't worry. Like.
I don't think anybody. We're talking about why is he in the class.
Yeah. Anyways, okay. Let's get back to graph because.
Working company.
Yes.
Why is the we want to same as we are here coming?
the thing is like when you
I'm not able to see actually.
your regular work is totally different
Can
than
you
what
get
you
to
are.
change short?
Oh.
Not able to see the
You
code.
have to clear you actually need to. You need to be brushing up all the time.
Oh.
Otherwise you forget those concepts.
Okay. So I was a test at Microsoft, and like I'm still a test at a company, and so today I was testing at a field. It's like totally different than what coding part is there. So like I test like helicopter products and stuff. So the first part of my office was like I was standing for 5 hours testing like, okay, what is happening to the system, what is happening over there, and all this other stuff. But I realized one thing at Microsoft when I was there, that whatever test cases were there was like I was in Internet Explorer. So in IE, the test cases are like this: open Internet Explorer, navigate to this site, touch this button, do this thing, and yada yada yada, close it. That's not how we use Internet Explorer, right? Like when I use Internet Explorer, I don't go and close every time I go to Facebook and then I go to CNN. I go to Facebook, do some actions, go back and log out, go to CNN, go to, I don't know, whatever, right? So if you think about it, it's actually a huge graph. Whatever user actions we are taking, it's a huge graph, right? Yes, I don't know. So the system, the testing system or whatever should be a graph. So I was thinking about it, and that's how I designed all the test cases over here also in my company. And I thought about it like, let's just make a graph. So what can happen is like, there'll be a graph, and let's say this is Internet Explorer for better, or like whatever. So I'm an Internet Explorer, I'll say this is my test case, so I will say that, okay, my test case starts from this particular, or forget about Internet Explorer, like my screen is there, like I'll show you what the screen is. So in that, like I get pressure, temperature, all these other things, and I can go to an app, I can go to a different thing. So every screen is basically a state. I'll say that, okay, start from this state, go to this state, do these actions. So what I do currently is I actually write a JSON file and I'll say that, okay, start state is this, end state is that, go ahead, do it. And then I have test cases like, okay, randomly pick whatever, wherever you want to go and try to go over there, do some actions and test it or whatever. That's actually a better testing mechanism. I don't know. That's how I think. And on top of it, Facebook introduced the graph search. I don't know what graph search is, but anyways, so Facebook is saying that, so people are interested, okay, what is graph? They might ask you questions. Okay. So if you think about graph, a graph is a bunch of vertices, right? And they are connected to each other. I don't know, like this kind of thing. So let's name them A, B, C, D, E, F, or something like that. So a graph will have a collection of vertices, okay? And the vertices, each vertices will have a bunch of edges. And it will say that, okay, I want to connect to you. And A will have a starting point of any edge will actually be itself, because I'm starting with, I don't care who is pointing to me. I just want to know whom am I pointing to. So that is what a graph is. So like when I had to implement it, I looked up at C++ graph, and like there was Boost library, which is really easy to implement, and I just use that. That's very simple. You don't have to do. You have to write just one line, and everything is done for you. So that won't be very helpful in the interview. So I created a class of graph based on that. So you can think of a graph in two different ways. You can think like, let's say this is there, A, B, C, D, E, F. So you can have an adjacency matrix. That's what they call. So you have a matrix. And you write A, B, C, D, E, F. And so this is basically a directed graph, because from A there is an edge going out. If there is no pointing or something, then that means it's an undirected graph. Right? And these graphs, let's say from A to B, you can add weights to these edges. You can say that, okay, this is, let's say 5, this is 10, this is 6 or something. So that is edges, right? So in an adjacency matrix, what happens is like A is there, A has a connection to B, which is 5, and A has a connection to F, which is, I don't know, whatever number, 6, 3, 2, I don't know, 4, 18, or 8. Right. So A has connections to, I don't know, you tell me. A has connections to F, and that is
FBB.
F, B is
10.
10,
B is 5.
B
Yeah,
is
yeah.
5. That's it. Like, I'm just giving an example. So, rest A connection.
We also have A to connection to A.
A to A, that is
That's
0.
zero.
I don't know. Like, if you want to create that, we can say A to A is there, or if we can say A to A is 0, because we are already at A. You can create it. I haven't implemented that. I'm just telling you this is one way of implementing a graph also. So there's no direct connection from C, so it'll be like, I don't know, you can cross over there. Similarly, you make all this matrix, and then you try to figure out, I have to go from A, and you like go through this matrix and figure that out. This is called an adjacency matrix. What I have done is like I have not implemented adjacency matrix. I have implemented adjacency list. Adjacency list is basically a graph contains a bunch of vertices. A vertices contains a list of edges, and an edge has a start point and an end point, and that's how we'll start writing the class. So a graph has list of vertices, and vertices has a list of edges, right? And edge has like a start and an end and a weight to it. So edge has start, end, and weight. Okay. So that is how we'll make a graph. So we'll start with the graph. We'll start with making the class of an edge. So we'll make class a edge. So edge has a public and a private. Public and a private, but this private has a member variable character C start and a character C end. And this is a very basic bare bones graph thing, implementation.
Yeah, if you see, like there are hundreds of.
There's too much.
People also use nodes over here instead of.
Yeah. So you can. I'm just implementing the
basic one.
very basic, because in interview you won't have time to implement the entire thing. So this is very basic. Okay. And then there's an integer weight. Okay. So a edge is the constructor. The constructor will have a character C start, comma, character C end, comma, integer weight. Okay. So yeah, pretty simple. And tilde a edge will delete everything, and then I have a function called character get start and character get end, which will get the start and the end, and integer get weight. So it will return the weight of that particular edge. Pretty simple. I'm not going to implement the. Let me see what I do. Yeah, I'm not going to implement the class for that. Like the constructor for this would just be C start is equal to this dot C start is equal to C start. This dot C end is equal to C end. This dot weight is equal to weight. So that's pretty simple. You guys know how to do that. Okay. So now we have implemented edge. Now we will implement a vertices. Vertices or node. Okay. Class a node. Okay. So public as a node. And the node will have a character which will be the identifier, so it is char ID, comma, I don't know why I took a data, but I just took a data just for the sake of it. Like, let's say you want to store something else on this particular node. So I have a data. If you want to add a complex data structure, you can add a complex data structure there. Sorry, I'm not using this anywhere, so we can just delete this also, or keep it. I don't know. Tilde a node will be the destructor. There will be few functions called void add edge, character C end, comma, integer bit. Why did I do? Okay. Void delete edge, character C end will delete the edge. Okay. Character get ID. We'll get the ID of the thing. And then there will be another function that I want to find all the neighbors. So I will have a std colon vector char get neighbors. So vector, for those of you who don't know, like vector is basically just an array list. So like it's just a list. So you can.
But it's a directed one.
Which one?
Vector.
The vector? No, vector is not it. It's just a list. It's just a list which can be resized. That's all it is. So it's basically array list. So, oh, that vector, that is a different vector, which has a direction and stuff. No, this is the standard template library. So I'll store all the characters of the neighbor, and boolean is visited. So I'll take a function which is have I visited it. I'll use it when I do the breadth first search or the depth first search for that. Is visited, and then there is a function called void set visited. Bool visited, which means that I'll use this to set that I have visited or I have when I want to clear it. But, and then there is a function called int get number of edges, which will get me all the number of edges that they are there. In the private, I have a character m underscore id, which is the id of that character, and then integer data, which I'm storing from here, and then there is std colon vector of number of a edges star. So I'm basically holding a list of edges. Just call m underscore edges, and there's a boolean value of m underscore visited, which means have I visited this or not. So far so clear? Do you guys understand this? Yes? No? Like, is there? This is easy. Like, yes, if anybody doesn't understand, let me know. Yes? Okay. So I will do what?
What's the last one?
The last line is boolean m underscore visited. So, yes, okay. So, should I implement? Should I do what people do in interviews, that they waste time implementing the? No, I'll just implement a few of them. So, you will. I don't know if you guys are understanding, so I'll just implement it very fast. Okay, so a node colon a node. It has a character ID, comma data. You'll make the data and all those things. Tilde a node will delete all the edges which are there in the thing. So do I need to write that? I don't know. Okay. Add edge void a node colon add edge character c end comma integer weight. Okay. So what will I do is, like, I have to add an edge from me to somebody else. So what I will add, the start would be me and the end would be this. So I'll say a edge ADGE star edge is equal to new a edge, and edge arrow huh? No, yes, oh sorry. This was taking a yeah. So, and this will take m underscore id, which is the id of this, and c end comma int weight, comma weight. So I did that, and then there was a vector of m underscore edges dot push back.
What was the end?
The m underscore edges is the vector.
C and
Which one?
the parameter, second parameter C and
C end is this.
so what was that parameter used
So
Not an end
for?
node.
The end.
so A to B, I have to make a node from A to B. I am at A, right? I have to add. So start will be my ID, end would be B's ID, that is C end,
Okay.
and the weight is like, let's say 6.
Yeah.
So 6 is there. And I have added an edge from A to B, and now I had a list of edges, right? So in my list of edges, I will push this edge.
Quick question.
Yes,
I suppose this is a directed graph, right?
yes.
How will you change it to undirected? Like, what will be the parameter?
And
I think maybe
and
we
will be,
probably you'll add two edges like A to B and B to A.
you
But
can do
will
that.
be double, right?
You can do that also, or you can,
But then edge will be different, right? Like this
yeah,
edge will be
okay,
different.
okay. For that, yes, I know what we can do. Okay, so in this, it's a very simple change, just a simple change to the edge data structure. So in the edge data structure, instead of C start and C end, we can say first and second. First and second. That's how it is implemented in the Boost library also. So if you want, so an edge is first and second. If you want to change that, like make it undirected, so in Boost, I don't remember right
Like
now.
if you're doing first and second,
Yes.
and let's assume that we have two directions, A to B and B to A, we still have to create two edges, right?
No.
No.
That's you're doing a
So-
redundant effort.
so,
You're adding the memory.
Yes.
So-
Okay.
But we still have to, let's suppose like weight from A to B is 2 and B to A is 4.
No, it's
It
No.
might not make sense, but it is possible.
No, in undirected, it would
It's
not happen.
So think about
No,
it
the
directed
weight will
as
be the
a
same.
road and directed as a airport kind of system. So airport, you can have a link between Seattle to Chicago, but
Yeah.
Chicago to Seattle can't be the same way. It can go to Denver and come back to.
No, that's not. If you are talking, there's two different things. One is we'll talk about that, but one is the directed and one is undirected, right?
That one
So
is-
in directed, like so, if we take an edge has first and second, right? So a list of what I will do is for A also I will add this list, and for B also I will add this edge. For A, I will add this edge to B, and for B also I will add
Oh,
this
okay,
edge to B.
okay. So it
Right.
will be in a B node. Okay.
Yeah, in the B node, and then when I have to find from B, I can say B, what are my different neighbors?
Yeah.
Give me that neighbor, and that will give the edge, and we can find that out also. So we have to make changes into this, but yeah, I mean this is, as I told you, like a very very simple, not a template, not a template kind of thing in which I can say unordered, like undirected or directed. Yeah.
When we are creating the node, we need to update the adjacency graph as well, right?
When we are adding a node, we add a node,
Yeah.
and then we add edges to that node.
Yeah, in the list we have created one tabular format, right? That has to also be updated, right?
The tabular form is no.
No,
That was adjacency matrix.
Yeah,
I'm not
adjacency
doing the
matrix.
adjacency matrix. This is adjacency list.
I think
List
this
is
is something
it.
like adjacency matrix already represent two-way directed one.
So
So I think,
basically,
yeah.
if it's a matrix, you do it by indicating a weight or a boolean value.
We will
We have
do-
A and B over there, so it's gonna be B to A and A to B. That's how we represent it.
So this is A and B to A will be that way. You have to
Two entries for
indicate
two entries for everyone.
That was the question, right?
Yeah.
So from A to B, if we have to figure out, so A to B is, let's say, 5, and from B to A it will be 3 or something, right? A to B is 5, B to A is 3.
I have one more question.
Yes.
If we have a scenario to add an edge in between two nodes, like A and B is there, in middle I want to add another one. So the weights are going to be changed, right?
Adding a new node between the two.
Yeah.
Add a new node, so A and B is there.
It's possible. B.
A and B is there, right?
In middle I want to place some C or K or something else.
Okay, so C is there.
Yeah, I want to direct from A to C and C to B. So
So
then
you'll add an edge to A from A to C, and
Yeah.
you'll add an edge from C to B.
B. Then C the weights from A to B is say 10. Okay.
A to B is 10.
10. Yeah. B to A is used to be 10 only.
B to A is
It's
10.
also should be 10. Now
Okay.
what I am doing is that I want my graph from A to C, C to B, B to A.
Okay. A to
C maybe like 4
4,
and then 6.
3,
Oh,
yeah,
whatever it may be.
sure. 4
Whatever
plus
it may
3, 7. Okay, you can reach B from
So
this way.
at that time all my things will be changing.
How? That is what we'll be doing the same thing. The Dijkstra's algorithm, that's what the algorithm.
There can be 3 different routes between the two points, right?
They can be
It
multiple.
doesn't have to add up to 10.
I'm going to break the direction from like A to B and B to C, right?
Yeah,
So A to B
direction
and
can-
B to A.
So direction can be anyways, right? It can be a longer direction, it can be a shorter direction. It should
No,
not
the
be a
directed graph is undirected graph is going to be directed graph.
I
The
have to
entire
go-
graph is going to
I have
change
to
now.
go from here to Seattle. I can go through 580. I can go through I-90. Right? There are two different ways. So I can go from here till Mercer Island, from Mercer Island to Seattle, or I can
Yeah,
just go.
my
Right?
question is like not that thing. How will we add in like the nodes
Okay.
in this type of graph?
Our question is, we had A and B, we have B, and there was one edge. Now we want to add a C edge between A and
A and B, not at
So,
that point.
but
We
here
add
coming-
that.
Hold on.
Not B.
The third,
I think-
I haven't implemented the entire thing. This
Right.
is just a node. The graph part, the graph that is, the first class was A edge, second class is A node, which I'm implementing. The third would be graph.
Let me
Yes.
try answering that one.
Yes.
So there won't be a single operation doing that. So if you want to achieve that, you probably have to create a C, add the edges, and then remove the B. So there are multiple operations doing the same thing. It won't be a one operation.
It won't be one operation. Yes. Okay. And like there is a function delete edge in this. So if you want to delete from A to B, you can call the delete edge this one, and it will delete that.
Or if you think like this operation is going to happen repeatedly, then you can have a
A different
another
separate
function which is kind of not very common with the graph.
Yes. Okay.
But that's also possible.
Anyways, so where were we? So we add an edge. We added it to the list of the edges. Okay. And then get ID. What is this function? Delete an edge. Okay. It's not a very efficient one. And
So actually, I just
Yes.
want to take some back actually.
Yes.
So we just discussed the directed graph, right?
okay.
So each node is actually containing their own set of edges. So A is going to have a edge which actually points to B. Similarly, if you want to direct from B to A,
Yes.
We
We
just
will
add-
have its own edges.
yeah. So we don't actually need to change, make any change, I believe.
Yeah, I don't think, I'm not
Yeah.
making any changes.
Okay.
Yeah,
No, I
I'm
thought
just
that was
doing,
like first and second
I'm just
one.
doing delete edge.
Okay.
I didn't get that much time to think and
No, I was thinking like, I was going back and thinking like, why we need the first node and second node? Probably we don't need it. This implementation is going to
this
take care of it.
is, this will take care of it. And I have tested this and run this, okay. Delete edge, what I'm going to do is for int I is equal to 0, I is less than m underscore edges dot size, I plus plus, I will say if, no, yes, I will get a edge star edge is equal to m underscore edges dot at I. So I get the one which is at the ith location, and I will check if edge arrow get end, which is the function which gets me the end part, is equal to C end. Then what I do is I will say m underscore edges dot erase m underscore edge dot begin plus I. I mean, it's just a the vector implementation. Then I erase that one, and then I will take the edge, delete.
Why did you do begin plus?
That's the iterator for, it's a vectors iterator. Like it's just an implementation detail. Like, so basically I could just say
At I position. if you
at
have-
ith position, but like in C, in vector, you have to write that way. Or I can take an iterator up here and do that. Anyway, okay. And then I delete the edge and I go away. Okay. Get ID is same, and I will write the get neighbors. Get neighbors. Get neighbors is just a
Going
function.
to return.
We will just iterate through this, and we will do a vector of characters. So it will give me all the characters. I'll just go through this, get the end of this.
Hey, I have one more question.
Yes.
When we are creating, we updated the m underscore add with push, right? We are
Yeah.
pushing the element. We have to pop it out also, right?
When?
When deleting.
When deleting, yes. So that is what I'm doing, edge. Dot erase. It's not push and pop. It's a different vector. It's a vector. So vector has insert or like push back. Push back is like putting it in the end, and erase means erasing at a particular location. So in vector, you're not thinking, it's not a stack or a queue. So vector is basically an array in which you can add. Adding it at the back is the best. So you keep adding at
Okay,
the
we
back.
can remove it
And you can remove at any position.
at any position.
Yeah, at any position you will just delete it. So that is what I did.
Okay.
So yes.
So it automatically takes care of the empty spot, like
It does the shifting.
The array list or a list function. or
It's
C++.
just a list or something, but I was doing it in C++, we don't have that. We can probably write a library which will do that, but we are not doing that today. Okay. So similar to this, we'll have some function which will put all the neighbors and character and put it in this, and it will return me all those things. Yes. And then is visited is just returning the is visited, and setting just sets the values. Okay. So at this point,
Hey, I just want to give one statement to
Yes.
the graph. A graph is nothing but a tree which is closed.
sure.
Okay, it will be having tree like all the nodes, parent, tree, parent and child.
Sure.
Okay,
Yeah.
when it is like wherever at any point if it is connecting to some other node, that will become a graph. A closed tree is a graph.
Okay.
Can you try the
Sure.
graph path from tree from?
I don't know. Maybe all the graphs are actually not trees, but all the trees are graphs.
Yeah, that's true.
Because tree is something like this. This is a graph because you can say that okay, A is pointing to B, B is pointing to C, D, E, and F and G, right? So everything is pointing. But so every tree is a graph because everything is pointing to each other. But if it is closed, then it does not become a graph. This is a graph. It does not become a tree, right?
Yeah.
So this is not tree. Yeah. Yes. So that is one thing. Yeah. Okay. So at this point, we have implemented edges. We have implemented nodes. Now we are going to implement the graph. click tilde a graph, and then void add node, a node star node, and a node star get node character a or character ID. Okay, so add node is adding a node inside that graph, right? And so a graph, yeah, a graph has a vector of nodes, m underscore nodes. So whenever we add a node, we add it to this list. Get a node, I will say that okay, this is the ID. It will go through this list and return me that node pointer. Okay, character get start node will get the start node. So let's say if we are traversing and then we want to traverse from a start node, so that it will give me the start node. Then it is character set start node with void, sorry, char c start. So this will set the start node to whatever we are sending, and so we need a character m underscore start node. So I have a start node which is there. Okay, and then we have a void.
So does that mean the IDs won't be repeated?
Excuse me.
So IDs will not be
Yes,
repeated?
the current implementation it is not repeated. It is not. Yes, very good point. And probably I will.
We can use GUID instead actually, but
We can use GUID, but it becomes too
Yeah.
long to identify. So breadth first search, which will start from character C start. Okay. Everything is pretty self-explanatory. When I call the add node, I'll have a node. It will be added over here. Get node will go through all this, and if this ID is found, it will return a pointer. Otherwise, it will return null. Get start node will return whatever is start node over here. Set start node will set this to whatever we are setting, and breadth first search we are going to implement that. Okay, so we'll implement the breadth first search. Okay, which is that's why I was looking at images of. Let's just take this one. So A, B, C, D, E. Okay, let's start pointing things. And D has one. Okay. Okay, so let's say this is a graph, right? So in the breadth first. Okay, so in breadth first search, what we do is we basically first we set everything to visited is equal to false, because we haven't visited anything, right? We set visited, so is equal to false. Then we take like the start. Let's say we are starting from A. Okay? So we take a queue, and it is empty in the start. We push A in the start node in there. Okay. Then we start a while loop and we check if we pop this out and we check if this node is not visited. So if A is not visited, then what you do is you set the node A to visited is equal to true. So we'll say visited, this is visited now. Okay, and then we get all the neighbors of this. We get all the neighbors, and then we push all the neighbors in the end. So we popped out A. The neighbors of A would be C and D. So we'll put C and D in there. Right? We get C and D. Now what we do is we pop out C. Check if C has been visited. It is not visited. We'll make this as visited. So C comes out. Then we actually add all the neighbors of C in the end. So this is a Q.
B and F.
Yeah, so it becomes B
Yeah.
and F comes in the end. Then we pop out D. D is not visited, so we make this as visited. And then we get all the neighbors of D, which is E. So you get E. Okay, now we pop out B. Is B visited? No, it is not visited. So we pop it out, make this green, and then we add all the neighbors in the end. So we add F and E.
Only
F is there. Yeah, that's fine. Like we will,
Yeah.
if it is not visited, if it is already visited, we won't do anything. Like you'll
Or
see.
like if
But
it is
F
listed,
is
we
not
don't even push in
visited.
the queue actually. We can also do
Sure, you can do that. You can do that optimization. But like, let's say if it is, but at this point F is not visited.
So we can.
At this point F is not visited, right? So we don't know.
Okay.
So we'll add F in the end. Okay. Next we'll pop out F. We'll make F as visited, and then we'll get all the neighbors of F, which is E. We'll put E in the end. Now we check. We pop out E. Make E as green, and neighbors, there's no neighbor, so we pop out F. F is already visited. We pop out E. E is already visited. We have traversed the graph in a breadth first search manner. Right? So the key to this is you basically do this in a breadth first search. In a breadth first manner is take a queue, add the first one to the queue, pop it out, get all the neighbors, put them in the back of the queue. I will implement this, and it should be very, very easy. They might ask you this question because in the book of Her Highness, it is written. She has vaguely mentioned it, so they might ask you. So we will implement this. Okay, with void graph breadth first search and C character C start. Okay. So first we will do is we will actually set the start node. So we'll say set start node C start. Okay. Then we will check if, I'm doing some check. If m underscore start is equal to null character, then return that whatever you sent was a horrible thing. You should not have done that. And then I'll say reset visited. In reset visited, what I do is I actually set everything to false. So nothing has been visited at this point. Then I will take a node star start is equal to get node C start. So I get the pointer of that starting node. Then what I do is, like, I just checked some other thing saying that if it is null, then say that you should not have done that. And then we make a queue. So we make a queue of a node star q nodes, which will be the queue which they are using. And then we'll say q node dot push the start node. Okay? So we push the queue in the start node, and then we say start node arrow set visited to true. So we have visited the start node, so we made it true. Then we'll say while not queue nodes dot empty, which means that while the queue is not empty at this point, there is a node which is there. That's the one node. So what we do is we pop it. So we'll say a node star node is equal to q nodes dot pop dot this front. The standard template library is a little bit different. Pop is not that. You first get the front and then you pop it. So we'll say q nodes dot pop will pop the top one. Okay, then we will check if not nodes node dot arrow is visited, which means that if I haven't visited this node, I'll just print the node ID. I'll print the node ID saying that okay, I have visited you, and then I will say node arrow set visited is equal to true. So I will set that okay, I have visited you now. Okay, then I will take all the neighbors of this node. So we'll say a node vector of character of neighbors is equal to node arrow get neighbors. So I will get all the neighbors, put it in this, and then I will actually write in an erase from the top.
Yeah, we can write something. I don't know.
That I won't be able to see.
Okay.
Okay. So, oh, sorry. Okay. Then I will do for int I. I'll send this code to you guys. So, for I is equal to 0, I is less than neighbors dot size I plus plus. I will get the node a node star node is equal to get node of neighbors of I. So I get the ith neighbor, I get the node, and I will check if not node arrow is visited, then I'll just print visiting node. I'll visit that node and I'll set it to visited, and then I'll push that in the end of that list. So that's basically what it is. I'll send you the code for that. So the only thing is you take the first one, set it to visited, add it to the queue, and then while the queue is not empty, pop the top one, get all its neighbors, put it in the end. If they are visited, then don't do anything. If they are not visited, just print it
I
out.
just want to share like one of the other implementations.
Yes.
If the get neighbors actually returns the list of nodes,
Yes.
we equal to that, then we don't need like getting a node out of the vector.
Sure.
So it's actually
Yeah,
something.
yeah. it's
And then it's based
yeah,
on
it's wasted of
multiplication.
one loop. Yes, I know that, but yes, it's not. It's a very simple implementation of graph which I implemented, and let's figure out a way for you guys to write the depth first search of this graph. Okay. So the only difference is
Stack.
use a stack. Use a stack and do that. Anybody wants to come on the board, I will help them. The code is exactly the same. It is exactly the same. My printer is not, I have to buy the ink for that, so printer is not working. But I will give you this thing.
That
You
can
can
be
look
signed.
into it and you can write the code.
That can be signed.
And explain to, no, and explain to the class, this is,
Signed.
explain to the class how it is working. Okay, let's just draw a graph. Let's just draw a graph. A, B, C, D, E, F. Okay, let's say this is the graph, right? Now you have to do a depth first search from A. Let's just walk through the thing, just so that we understand. Okay, so now what we do is we take a stack. We take a stack. And we take A. So we put A over here. And we make the set visited is equal to true. Right? And then what we do is we pop out A and we check the neighbors of A. So who are the neighbors of A? B and C. So A gets popped out, B and C comes in there. Okay? And then we pop C and we make C as visited, and then we add the neighbors of C. So who are the neighbors of C?
F and A.
F.
A is already visited.
And A is there. A is already F has A. No F. Okay. C. Yeah. Okay. F and then who else? Is there anything else? No. Okay. So we put F in there. Now we pop out F and we make F as visited
Just
and add neighbors. So D.
Yeah.
D out.
D is there. Only D is there. Right?
D doesn't have anybody to visit.
D doesn't have anybody, so we'll pop out D, we'll mark D as visited. Now we'll go back to B. So now B gets visited and add the neighbors of B. B's neighbor is, B got, yeah, B's neighbor is E. So now E gets visited, and this is, so if you see, we have visited first A and then C and then F and then D and then B and then E. So we have gone one way and then we have gone. So this is
Just
a,
one thing, like in a graph,
yes,
it can be disconnected. Like let's suppose we have T,
Yes.
which has no edges, no. So it is
yeah, let's say if there was T which was connecting to
No,
E
no,
and
no,
F.
there's a T which is not connected at all.
Yes,
Then how do you go there?
so we won't be
Yeah, so-
traversing to that.
Yeah, we won't be traversing to that one, but it is traversal should be all the edges, all the nodes.
Okay.
So in that case, we need to actually put another condition
Mhm.
that if going through the list of nodes in the graph and seeing like if it doesn't have any edge, then just print it out. Otherwise, that
We will not have any disconnected web.
Graph, you will always have a
Yeah,
starting
sorry,
point.
graph.
Yeah, graph with the starting point A, you will never get to the T. Is that correct?
Yes.
It doesn't mean that T should never be traversed.
Yes.
Why?
it
How
should
can
not
you
be
traverse?
there.
So starting
Not
point,
because it's not a part of graph.
it's
So-
disconnected, right?
So in the graph, you have list of nodes, right? In the list of nodes, you have T. But he
List
doesn't
of
have
connected nodes.
Yeah, it's a connected
Actually,
node.
Not disconnected.
yeah, actually,
It's a
like,
disconnected graph.
a
that is-
disconnected graph. That what it is like. It might not
Yeah,
have
in
any edge.
disconnected
It might not
graph
have
can
anything
have
coming to it.
separate.
That's a special type of thing. actually.
that's a special. Actually, that book over there, like it has a lot of description. I will actually take out. It's difficult to read. I will actually take out the description of it says that okay, this is a directed, this is a undirected, this is a connected, this is a partially connected, and all this other things. So I will send the description so that at least we know. So okay, so we did that. So now we know how to yes.
If a graph has weights, do we do the depth first and?
The weight is like if you had seen actually the edges had a weight.
No,
Yes.
my question is like if they have a weight, so do we need to consider weight while doing breadth first and depth first search or just?
No, breadth first and depth first search. The weight part will come in the Digectors algorithm where you actually have
That
to
is
find the
called the,
minimum.
if the graph is having weights, that is like a weighted graph. That is
Yeah, that is weighted graph. What she's saying is
Yeah.
in the breadth first or depth first,
No, we don't consider.
we actually don't consider that. The algorithm is different for that, right? So we'll come to that.
So, is there any strategy like for these graphs we should use BFS or for these graphs
The question generally would be like give a because
traversal thing?
yes, because she who shall not be named in her book it is breadth first search. So most probably they'll ask you breadth first.
So
So, but like,
basically,
based on the- sorry.
the reason for this question is, in graph traversal, most of the questions are related to finding the weight. Traversing the graph from point A to point E and find the shortest path. So shortest path will be associated with the weight, and if you go with the depth first search, you will find a path, but it might not be the shortest one because you end when you hit the end. But with the BFS, you have that opportunity because you actually traverse. Think about a tree. You traverse like A and across, and then across. So you have an opportunity to choose the best one. So that's why you choose the BFS.
And another thing is like they might ask you a question like okay, Facebook is there, right? Let's say I am friends with these 4 people and you are friends with those 4 people. And let's say I'm not friends with these 2 guys, right? So if I start finding his friend is over there, so there's a high chance that my friend's friend is there. But like I go your way and I can keep going, but I won't find you. But the degree of connectedness between my people will be less. So that's why
We should go for that.
breadth first.
Right.
Breadth first. So that's why in Facebook or something like that, you try to do a breadth first.
Another example would be a game theory. So if you are playing a chess, which are the possible moves for any possible given move? So that can only be possible if you have a BFS.
Yes. Okay. So
Can
they
we,
take
can we implement a breadth first without having to?
I haven't seen that, but
We know that we can implement